How do we differentiate y is equal to cosine of the cube of 2 minus t? Recall that the derivative of cosine is negative sine, so we have negative sine of 2 minus t cube, and then we use chain rule for 2 minus t cube, so we have 3 times 2 minus t squared, and then chain rule further for 2 minus t, so we have times 0 minus 1. And if we simplify, we have this one. How about if we are considering functions of several variables? For part 1, suppose we have a function in terms of x and y, where x and y are functions in terms of t. If z is equal to f of x, y, where x and y are functions of t, then the derivative of z with respect to t is given by this formula for dz over dt. Observe that the first factors of both terms, the one which are highlighted, are the partial derivatives of z with respect to x and y. Meanwhile, the second factors, highlighted in yellow, are derivatives of x and y with respect to t. Graphically, the tree of dependency is given by this one. The first term in the formula for chain rule is represented by the violet path in the graph, plus the second term, which is represented by the green path. For our first example, let us find dz over dt if z is equal to x squared y, and x is equal to t squared, and y is equal to t cubed. Using our chain rule formula for dz over dt, first let us solve for the partial of z with respect to x. Since we are solving with respect to x, therefore we treat y as a constant, and so the derivative is 2xy. For dx over dt, just the usual derivative, we have 2t. Plus the partial of z with respect to y, so this time let us treat x as constant, so the derivative is x squared, and dy over dt, the usual derivative of y is 3t squared. This already serves as our final answer. But for our example, we can still write x and y in terms of t, since this is quite simple, so let us copy it, and then substitute x is equal to t squared and y is equal to t cubed, and if we simplify, we obtain 7t raised to 6. For our next example, we have z is equal to secant x squared over y, with x is equal to 2 raised to t and y is equal to ln t. Let us find dz with respect to t. That is a correction, that should be dz over dt. We have this formula of dz over dt. For the partial of z with respect to x, we need to treat y as a constant, so we just copy y in the denominator, then solve for the derivative of secant x squared. The derivative of secant is secant tangent, so we write secant x squared tangent x squared. Then use chain rule for x squared, so we multiply times 2x. Next on the formula is dx over dt. The derivative of 2 raised to t is 2 raised to t ln 2, plus partial of z with respect to y. So here, we treat x as a constant, so we just copy secant x squared, then get the derivative of 1 over y. The derivative of 1 over y is negative 1 over y squared. Lastly, the derivative of y with respect to t is 1 over t. There is no need to write x and y in terms of t, especially if our answer is very long, so this can already serve as our final answer. Before we proceed, pause the video and try to solve for dz over dt given the following functions. For the second part, suppose we have function f of x, y, and x and y are again functions of two variables s and t. Then the partial derivative of z with respect to s is given by this, and this for with respect to t. Observe that they are very similar with the first part, except that the second factors for each term are partial derivatives instead of the usual derivatives. And the tree of dependency is given by this graph. For the partial derivative of z with respect to s, the first term is represented by this blue path, and the second term is represented by this yellow path. And similarly, we have this for the partial derivative of z with respect to t. For our first example here, suppose we have z is equal to e raised to xy, where x is equal to 2s plus t and y is equal to s over t. Let us find partial of z with respect to s at the point negative 1, 1. Let's solve for the partial of z with respect to s using the previous formula. So here, first we solve for the partial of z with respect to x. So let's go to z, that is e raised to xy, and treat y as a constant. So just copy e raised to xy and multiply by y for chain rule. Next, the partial derivative of x with respect to s is 2 since we are treating t as constant. For the second term, the first factor is the partial of z with respect to y. So that is x e raised to xy. And the partial of y with respect to s is 1 over t, since we are treating t as a constant. To simplify, let us factor e raised to xy in our expression. We are given the point -1, 1 for the ordered pair s, t. Using these values, we solve for the value of x, y. If s is -1 and t is 1, then x is equal to 2 times -1 plus 1, that is -1. And y is equal to s over t, so that is -1 over 1, or simply -1. Then we plug in these values for s, t, x, and y to solve for the partial of z with respect to s at that point. And if we simplify this, we get -3e. For our next example, let us find the partial of z with respect to both s and t, given z is xy cosine y, x is s raised to t, and y is s times ln t all over t. Before we consider the chain rule formulas for the partials, let us get first the partial derivatives of each functions with respect to their corresponding variables. So first, let us consider the function for z and solve for the partial derivative of z with respect to x. That means we treat y as a constant. If y is a constant, then so is y cosine y. Therefore, this derivative is equal to y cosine y. How about the partial derivative of z with respect to y? In this case, let us treat x as a constant. So since x is a constant, let us just copy x. Then get the derivative of y times cosine y. That is a product, so we use product rule, left the right plus right the left. So for the first term, left the right, we just copy the left factor, that is y. The derivative of right is the derivative of cosine y, which is negative sine y, plus right the left, so copy right, cosine y, and then the derivative of left, the derivative of y with respect to y is 1. And we get this if we simplify. Now we move on to the partial derivatives of x. First, we get the partial with respect to s. So here, t is a constant, and thus the derivative is ts raised to t minus 1. On the other hand, the partial of x with respect to t is s raised to t times ln of the base s. This is because here, s is treated as a constant. For our last function y, the partial of y with respect to s is ln t over t, since t is treated as constant, and the partial of y with respect to t, so here we treat s as a constant, so let us just copy s. Then get the derivative of ln t over t. That is a quotient, so we use quotient rule, low the high. So low, copy t. Derivative of high is 1 over t. Minus high the low, so copy ln t. Derivative of t is just 1, all over t squared. And if we simplify, we have s minus s ln t all over t squared. After we solve for all the partial derivatives, we now use the formula. First, the formula for the partial of z with respect to s. The first factor in the first term is the partial of z with respect to x. So we have y cosine y. After x is the partial of x with respect to s. So we have ts raised to t minus 1. For the second term, the first factor is the partial of z with respect to y. So we have that one. Times the partial of y with respect to s. So we have ln t over t. Now for the partial derivative of z with respect to t, observed in the formula that they have the same first factors. So copy the first factors, partial of z with respect to x, and partial of z with respect to y. However, for the second factors, in our first term, instead of partial of x with respect to s, we have partial of x with respect to t. Similarly, on the second term, we have partial of y with respect to t. For the second exercise, x and y are functions of r and t. And for the third exercise, x and y are functions in terms of u and v. Before we proceed to the last part, pause the video and try to answer these exercises. For the third part, we observe here that we can still use chain rule for more variables and even for higher order partial derivatives. For example, suppose we have function u in terms of x, y, and z, wherein x, y, and z are functions in terms of p, r, and theta. Let us find the partial of u with respect to r. The function u is in terms of three variables, x, y, and z, so we will get the sum of partial derivatives of u with respect of these three variables. Moreover, for each of these partial derivatives, we will multiply it with the partial derivative of the variable with respect to r, and thus we have this formula. Now let us solve for the partial derivatives. The partial of u with respect to x is 2x times the partial of x with respect to r is p cosine theta. Next, we have z times p sine theta plus y times 1. And this is our final answer. For our last example, let us find the second order partial derivative of z with respect to r if z is equal to x squared plus xy, with x equal to 2r minus s and y is equal to r squared plus s. Let us solve first for partial of z with respect to r using chain rule. The partial of z with respect to x, so here we treat y as a constant, so we have 2x plus y, times the partial of x with respect to r, which is 2. For the second term, the partial of z with respect to y, so here we treat x as constant, so we have plus x, times the partial of y with respect to r, so treat s as the constant, so we have times 2r. If we simplify, we have 4x plus 2y plus 2xr. Now, the partial square of z all over partial r squared is equal to the partial derivative with respect to r of the partial of z with respect to r. We already solved for the partial of z with respect to r, and so we write here. Then let us get the derivatives of each term with respect to r. For the first term, 4x, just copy 4 and multiply it by the derivative of x with respect to r, which is 2. Similarly, for the second term, copy the constant 2 and multiply it with the derivative of y with respect to r, which is 2r. For the third term, we have the constant 2, so copy the constant 2, then get the derivative of xr. Observe that x is a function with respect to r, and thus we have a product xr, so we use product rule. Left, the right, the derivative of r is 1, plus right, so copy r, the left, so the derivative of the left term x with respect to r is 2, since x is 2r minus s. And if we simplify, we have 8 plus 8r plus 2x. For our last set of exercises, please solve for the following partial derivatives.